Hello everyone, can you hear me? Doesn't seem like there is. Oh, all right, now I see some people that are connected. Can you tell me in the chat if you can hear me and if you can see me and see the slides? Hi, hello for those that are just joining us. Yeah, great. Thank you for the confirmation. So this workshop will be in English, and we'll talk about deep learning. It will be a quick introduction to deep learning. We'll discuss about some use cases and the general architecture and behavior of neural networks, dense neural networks, and convolutional neural networks. There is no real prerequisites for this workshop, except maybe for some knowledge, general knowledge about machine learnings and some different types of machine learning problems. But yeah, it shouldn't be too much technical. So yeah, you should be able to follow along. If you have questions, do not hesitate to ask them on the chat. So yeah, as I've said, it will be in English, but you can also write questions in French if you want, and I will answer in English. Great, let's start. So yeah, a quick summary. So I'm gonna start by discussing about some use cases and some general usage like that we can make of neural networks. Then we'll talk a bit about different types of data that you can use with deep learning, and that probably you need deep learning in order to use efficiently to train a model or have an artificial intelligence approach. And we'll discuss also about the definition, the mathematical definition of a neuron and how it works inside of a complete neural network and dense neural networks and convolutional neural networks for images. And once again, if you have any questions, do not hesitate to ask them on the chat. So some use cases. We'll start with some usage of deep learning for computer vision for image here classification. It's maybe the most common example. Everyone or almost everyone knows that when we have images, we cannot use like traditional algorithms or statistical techniques. It requires some more advanced model and, for example, deep learning. There is two types of classification. Just the let's say basic image classification. Here we have an image of a dog with a plant. Classification should just answer one this type of questions. Is it a dog? Is it a cat? Is it a car? Basically just classify the image. The other type of classification is multi-level classifications. We do not see that often, and requires a bit more work on the network. But basically the question we would want to answer is there a dog, is there a cat? So you can have multiple label for one image, and it's probably the most um, common example for usage of deep learning. You know probably that when we have what we call unstructured data, we'll talk a bit about that later. When we have unstructured data like images or text or audio data, we will use deep learning. So in that case, it's example with computer vision. There is like multiple things that we can do with images and deep learning. We just saw classification. We can have try to solve a regression task. So that means extracting some quantitative value from the image. For example, the coordinates of what we call a bounding box to detect an object, and for face detections, face detection problems. We can also try to predict some characteristics about anger, happiness, or some information that we can extract from the image. So yeah, once again, when we deal with images, we can do pretty much everything we want to do with neural networks. It's really flexible. I will talk a bit about the general architecture of networks later, of course, but here are just some other examples. Also, yeah, probably known by most of you, the example of segmentation or object detection that are used for autonomous vehicle or surveillance camera, for example. Segmentation, though, it's like a classification, but almost pixel by pixel. It's really to detect precisely objects, and you have yeah. So that's for the segmentation, and for object detection, it's really also yeah, try to predict the object and to delimit an object with bounding boxes. This is the output of a really famous model that's called YOLO, for you only look once, and that allows us to detect multiple objects on one image with the classes associated to each object. So that, as you can see, these two solutions are really precise and can be useful in a lot of areas. We have also the landmark or key points detection that can be done using images and deep learning. So it's same idea as the regression for the bounding box, but it's more precise. Of course, you have more coordinates, more informations. For example, here the key points for the faces that you may know if you're using filters on social media, for example. And you have the version in 3D. I think it's a solution by Google. This one, and it works really well. It's open source. Maybe I'll send you a link if you want to try. It's pretty fun. But yeah, basically, when we have images, we can do anything we want. We can also do face recognition, so identification of people, or object tracking. So for videos, so it's the extension of object detection with YOLO, which is so on the previous slide for videos. So you have a continuous flow of data of images, and you want to just follow some objects. Here it's on a football field, but you can really do a lot of things. This is maybe the most recent approach, or it's an estimation of the depth or the detection of object in either a foreground or background. And this can also have a lot of usage in different technology or in engineering. For example, here it's mostly for fun, but you have a lot of different applications with images, and basically you need deep learning solutions to extract the most information about images, and it's really like maybe the most the research field in deep learning where there is the most work today. So with the augmentation of the resolution of the images, and the fact that we have, of course, images everywhere, and cameras, and a lot of I don't know, pictures or usage of surveillance camera or for different kinds of technology. So it's really challenging, and you really basically need deep learning models in order to extract the most features, the most information from these kind of images. And we'll see why in a few minutes. There is also a quick video to show you more advanced example with autonomous vehicle. You have like real-time detection of different objects. It's like it's object tracking basically, but more advanced, because you have a detection of the lines of all of the objects, the traffic signs, and so on. So that's the video from Tesla. They probably have the most advanced object detection and object tracking solution for autonomous vehicle. And actually, their solution and algorithm are for most of them public and open source and access. You can read the research paper if you want. It's a bit technical, but really interesting. All right, so that was for computer vision. The other really used or explored domain of deep learning is natural language processing. So when you have to deal with text data or audio data, and you have some solutions with classical machine learning techniques when you have text data or you have some text mining or extraction of information based on yeah text. You have some solutions that works pretty well without deep learning. Maybe um, some of you already know about that, but oh, it seems that the mic is not. All right, I'll just try to speak louder. Um, but yeah, maybe some of you know already some solutions with text mining or classical machine learning techniques. But when you have like more complex text data, like articles about really specific topics, or when you have audio data, when you have recording of people talking, or when you need to extract really precise informations or classify really precisely some text, some reviews or stuff like that, it's you need to have an algorithm that is able to almost understand the meaning of the sentence and the link between the different words, and you need to have some specific deep learning methods in order to do that, because yeah, with the traditional approach and statistical techniques of standard machine learning, you lose the link between the different words. So if you, yeah, for those of you that already know about machine learning and when you use data frames, you have your features, and your algorithm try to find a mapping between the features and the target label. Let's say we would here try to do some text classification. We have an article with some text, and we want to put it inside the one category, here technology, sports, or entertainment. And so you will have if you use classical machine learning, you will have one word will be one feature, and your algorithm will try to predict based on those words the right target label for classification, and but it will not see the link between the different words. So it's really not that efficient when it comes to yeah, technical text, or if you have long sentences or a lot of different words. So you need models that can really yeah keep the sentence in the right order, the link between the word, and that can know if some words are related, or if they are um, commonly used together, or if they are related to a field, a specific field or topic. And for that, yeah, you need deep learning. So that's, yeah, the first example is this one, so text classification. The other one could be post tagging, post for part of speech tagging. The idea is that you can associate to each word its usage, its syntactic role in the sentence, and that can also be really interesting. And you could do both actually. You could try to detect the meaning of the word in a sentence, and why is it in this sentence, and what's the link between the different words. And then with another model, you could try to do text classification based on this more complex representation of the sentence. Same idea for name entity recognition, NER, and parsing. So NER is the goal here is to extract really specific words that are related, for example, to I don't dates, or famous people, or places, or historical events. And so you extract the key information from the text. And for parsing, it's yeah, close to post tagging. You, yeah, try to to know, yeah, the role or the purpose of each word in the sentence, and to understand how the sentence is written, and what's the purpose of each word and how they're related. And so, yeah, all of these techniques are really interesting and really challenging, and you really need deep learning models, and more precisely what we call recurrent neural networks, to deal with this kind of problems. Um, so you need, yeah, what we call recurrent neural networks, one kind of network that can keep this links, this information between the different words, and that doesn't just look at each word one at a time. And it's one type of model, and it's used with what we call embedding. Embedding is the way you represent the words, the way you um, transform the words into a vector that the model can understand. Of course, it's the same as in machine learning, and it was the same for the images. So we have eyes, and we can read, but the model cannot. So you have to uh, choose a way to represent the words. So that's called a word embedding. And based on this vector representation of the words, you have one model that knows how to interpret these embeddings, and how to, yeah, answer try to solve the problem you need to solve. So yeah, there is a question on the chat. Are specific Python packages for NLP and text recognition? Yeah, there is some. There is some packages for uh, to extract some informations about text. You have NLTK. Maybe I will send you some links. But you have NLTK Spacey, for example, that, yeah, are just really. You have fast text also, but yeah, these are really packages to extract this kind of information. You can just run a function, and it will give you this kind of output for NER, for example, or post tagging, or text classification. It will do the work for you. Um, yeah, and otherwise, you need to create a deep learning model, or called a recurrent neural network. And in order to do that, we will see some frameworks in a few minutes. All right, so that was a short introduction and discussion about some classical usage of deep learning, and why we need some more advanced techniques to deal with this kind of, let's say, strange and unstructured data. So more generally, deep learning can be seen as a subpart of machine learning, that itself a subpart of, sorry, it's in French, but artificial intelligence. Um, and yeah, it's a simple representation. It's a bit more complicated than that. The model nowadays are far from intelligent, and we just have some data and some statistical and mathematical methods to create um, a link, a mapping between our input data and the target value we want to predict. So yeah, it's far from intelligent, but let's call it that. And so deep learning, it's one specific kind of models, the neural networks. So it's basically also statistical approach and mathematical, mathematics applied to data, to data manipulation, or to data science in general. And yeah, so yeah, there is a question on the chat. Is it suited for any language or only for English? Yeah, it was for the packages for or text manipulation and some prediction. It's a good question. The fact that, maybe let me go back to this slide. The It really depends. These packages, the one I mentioned, can be used with multiple languages. Not all of them, I think, but the yeah, it's actually a really interesting question, because all the languages are built completely differently. it's not even always the same alphabet or the same characters. So it you have some models that are suited for different languages, and for some of them, let's say, if you want to work with, I don't know, Chinese or Russian or an Arabic language, you will need probably to if you want to design a model from scratch, you will probably need different models for each of these situations. These packages and yeah, these packages can be used with different languages because yeah, there is some different models that are working backstage and can give you the solution. Same as if you use like translation tools, for example, Google Translate or DeepL. There is a lot of models and they use a lot of different data from different languages and so on. But yeah, if you want to design a model from scratch, you will have to take into account the fact that there is some difference between the languages, and you will have to deal with some specificities. And same as yeah, the raw presentation you need to have with the word, the embedding I talked about earlier, will be different um, between different languages. So yeah. Yeah, there is some great answers in the chat. Yeah, you. Yeah, I won't go into the details, but indeed, when you build your own model, you can create your own dictionaries. You can specify a list of words that you're going to use based on the dataset you will be working with. So it also really depends on what you want to do and what is the kind of data you want to use. Of course, for Google Translate, they took almost all of the text on the internet, so that's convenient. But if you need to work on a I don't know, specific topic in a specific language, you will use a fixed dictionary, a list of words that you will represent with the embedding, and that you will use to train your model. Yeah. And yeah, indeed, it is a huge amount of work. There is some function to automatize some of that. The way you choose your dictionary and how you train your model. And yeah, there is a lot of solution to make this creation of the data you will use to train your model and the way you build your model. So there is some frameworks. I will talk about Keras later, but basically you do not just write the list of words and the matrix product that you will use to train your model. You have like this whole architecture or this whole frameworks that already exist and that really facilitate the um, creation and training of these models. But yeah, let's come back to the different types of data. So we talked about images and text. There is also, of course, some yeah, sorry, JSON data or like dictionaries. You can have audio data recordings, and this is what we call yeah, not for the JSON, but for the images, the text, and the audio or the video. It's called unstructured data because you cannot have this like clean representation and something that's already suited for yeah for modeling. And you cannot just say all right, I have an image and I will give this image or this text to my model, machine learning or deep learning. It just won't work. You have to choose a way to represent your data to have like yeah, a structured way of representing this data for sorry, the comment here is in French, but not that interesting. Anyway, you for the text data, we talked about embedding, so you need to transform the text into a vector representation that will be used by the model. For the images, actually, the images are just matrices of pixels, and these matrices can be used with a special type of yeah, a special type of manipulation that we call convolution product, but yeah, it's not as easy as if you had like a clean data frame like this, or JSON structured data. So that's why basically we need another type of models, the deep learning model, the neural networks, and that's why you cannot use just classical machine learning techniques. With classical machine learning algorithm, for those that are familiar with it, you have like in general this kind of data. So you have different here transactions, but it can be individuals or examples. And for all of them, you have different features, the explanatory variables, and you have a target. You want, based on this data, to try to predict something for what we call supervised learning. But anyway, and the model will give like a weight and importance to each feature, and will tell you based on the value of each feature if the prediction is this one or that one. And you can not just use the same computation, the same mathematical techniques when you have matrices of pixels, or even when you have vectors of text, because yeah, it's just not same kind of explanatory variables, the same kind of features. So you need to do something else. We could, for the metrics of pixels, the images, we could just what we call flatten the images, just put every pixel, just take a list of pixel. One image will be a super long list of pixel, and we could have this kind of representation in a data frame. But yeah, you understand that we lose every information we have on an image if I take these nice images, these nice pictures, and I just list all of the pixel, I won't see anything, and we wouldn't know if where the sea or the sky or building or anyway or yeah or anything else, we wouldn't know. And so it's the same for the model. The model needs to have clear representation of the data, and so yeah, we just need another approach, and we cannot use traditional machine learning techniques when you have this kind of unstructured data. Um, More generally, when you have, yeah, let's stick with supervised learning, but in the traditional approach of machine learning, you have, so your input data, here it will be, let's say, an image, or some features. The feature extraction will be done by the data scientist. So some works, we call feature engineering. You will manipulate the feature, maybe remove some of them, or select the most important ones, or apply some transformation, normalization, standardization, and so on. And then you would have your machine learning model. Um, and this machine learning model will, based on the features you gave him, try to predict something. That's the classical machine learning approach when you have structured data. And with deep learning, it's not working like that. You have your input, you have the data, and the model will do the feature extraction by itself. It will learn to take the most important information in your data. It will learn how to transform the data into something else, to read it, to understand it, and to give you an output. So yeah, it's quite different, and that's also why we can use any kind of data. It's because yeah, it's really flexible. We can really have the architecture that we want, and it will give us an output, maybe a bad prediction, but it will give us an output, and it's much more much more flexible, and you can use different models with much more different types of data than machine learning. That's machine learning, you really need this representation in a data frame, or something similar to a data frame with your features that are well defined. So the neural network looks like this. Probably all of you already knew about that, but it's it's built in layers. So that's the simple architecture of what we call dense neural networks. Um, it's built in layers. So you have your input layer. The input layer just takes the data, as input, and you have yeah, basically products between. Maybe I'm gonna go directly to the next slide, but you will have for each layer a product between your input and the values of the layer, what we call the weights of the neurons in each layer. And this product is just inspired by our yeah, the neurons in our brains. The neurons in our brains take some informations, and there is like a status of the status of the neurons, and you have like this information that comes in, and if it's let's say a good information or something interesting, the neurons send a signal, an electrical signal, and here the idea is exactly the same. It's the neuron have weights that will be learned during training. The model will try to find the best weights, and you will have yeah, I said products and not dot products because it's not always dot products, but yeah, for dense neural networks, it's you have yeah, dot products between the input and the weights, let's say the knowledge of the neuron, and this operation will be yeah, will be done for each neuron, for each layer, and the output of this computation, this product, will go through what we call an activation function f that will return an information to the other cells or the other neurons of the network. And yeah, basically you do that for multiple layers and multiple neurons, and you get finally an output. And this output can be, as we've seen earlier, something like a classification or a quantitative value. If you have regression, you can have multiple outputs, of course, because it's really convenient. You have this, all of these product of matrices, either the products of or convolutional product we'll see later, but it's really convenient. You can really add the different neurons that you want and have the architecture, the number of layers that you want, because yeah, it just stays dot products and activation functions, and it's yeah, really convenient. So that's why we can use different kinds of data. So that's the simple representation, of course. Here, it works for let's say the simple kind of data. When we have a text, as we've said, we need another representation that takes into account the order of the sentence, the order of the inputs. And when we have images, we need a representation that can go through a matrix of pixels and not just do a dot product between vectors of inputs and weights. So that's a bit more technical, but the general idea is this one. You have input, and yeah, you want your output, and so all of this information will go through the network, and the network will try to learn the best yeah, the best knowledge, the best weights for each of its neurons to um, have the right activation, the right transmission of information between the input and the output that you're searching for. um, yeah, I just saw the messages on the chat. Yeah, for this representation here, it was just for an algorithm. It was yeah, maybe a wrong choice of visualization, but it was not a neural network. All right, and yeah, if you understand that this slide, you understand neural networks. Congratulations. Yeah, basically, you have an input, you have actual weights that are learned, and this learning will go through activation function that will return a value, and this value will be used by the next layer for the same kind of computation, and so on. And so you have your input, and at the end you have your output. And if the model has like the right guess, the right prediction, it means that the weights are the right ones, so no need to change them. But if the model is wrong, we will have what we call backpropagation. So the model will just look back at the different weights and adapt the values to correct the error to try to approach the right value. yeah, that's what we call the forward propagation. It's when the models read the data and does this kind of computation and activations to try and predict something. It's the forward pass or forward propagation, and the model just looks at its prediction and the target output, and if there is an adjustment or a modification that's needed, it does like look backward and adjust the weights accordingly. Great question from Pascal. Are neural networks always better in any algorithm, or may other ML algorithm be better than neurons in some cases? Actually, for structured data, this kind uh, of computation is not always better. Great answer. I'm gonna um, just show this answer. The no-French theorem is really famous in statistics and in machine learning. It means basically that you cannot have one algorithm to rule them all. You cannot have one better algorithm for any case. And for deep learning, it will be always better for unstructured data, almost always for unstructured data, but not for structured data, because structured data you have this um, yeah this uh, these features, and you have so many different techniques and approach of traditional machine learning, either just weights learning was for regression or logistic regression, for example, for linear or logistic regression, and you have like trees to find the best parameter to split different categories, and you have so many different techniques that can fit for one kind of problem, or so it's mm, let's say more diversified than just these products and this activation function. This architecture is almost always better when you have complex data, because as I've said, it can like read images more efficiently, or have a better understanding of the link between images that can follow each other in a video, or words that are in a sentence. And so, for unstructured data, it's better. For for unstructured data, it's better almost always. And for structured data, it's rarely better. In most cases, there is not enough complex link between features and outputs, and so you do not need neural networks. Actually, yeah. Um, So just to show you a bit of the Keras framework for deep learning, for those that are familiar with Python, it's really easy to implement. You just add some layers, and you say, yeah, I want this number of layers with this number of neurons, and I want this kind of activation function to compute this kind of value, and you basically just compile your model, or define your model and train it with specific parameters. I won't go into the details here, but just to show you that with 6 lines of code with the import, you can define this the model here on the right, and it's really easy. And that doesn't mean the model will be the best one. If you have you could ask me, how can we choose the number of layers? How can you choose the number of neurons for each layer? The answer is, in general, you do not know, and you do not choose the best solution at first. You have to try so many different things and combinations. But it's really easy to implement, and it will automatically be like optimize the computations and the matrix products between the different neurons and layers. So it's really convenient. You don't have to define all of the forward propagation and backward propagation. It just does all the work easily. And you can add some different tools to try to find the best parameters, or monitor or control the training of your network. That's really interesting tools to use. But yeah, it's easy to implement, but it's really hard to find the best model. If you're familiar with machine learning, you know that we can we can choose an approach, we can choose one kind of model, and for this kind of model, we apply basically a grid search or other optimization technique, and we find for this specific model the best parameters. For deep learning, it's just too computationally costly to just do a grid search because there is so much possibilities. The number of layers, the number of neurons for each layers, the different activation function, the parameters for the training, how much data at a time you want to take, the size of what we call the batch, the length of the training, and yeah, there is no easy solution to find the best parameters. Um, yeah, so yeah, to answer the question, we can, in theory, use a grid search, or yeah, or random search, or this kind of techniques, but it just takes so much time, and it's just so costly that it's not in general what we use. There is some research about how it's called NAS, neural architecture search, to find a way to just um, yeah, try this kind of search efficiently and to find the best yeah, best architecture. But yeah, it's really really it's not, it's still yeah, under research and under development. Maybe in a few years we could have something as smooth and as easy to use as the research, but yeah, not today. The In general, we use what we call transfer learning, and that means basically that we will go through the literatures and some research paper, and that we will find a model that we know works well with kind of data that's close to what we're going to deal with. And you take this model as a baseline, and you start working with this model. You do not create from scratch your deep learning model, or you do not create from scratch the embedding, the representation of the words, or the way you're going to manipulate the images. You just yeah, it can seems like like you stole the, yeah, like you're stealing the work of other people, but in deep learning, it's perfectly normal. Everyone is doing that. You just, yeah, it's called transfer learning. You just look at the literature and just find something that a problem that's similar to yours, and yeah, you start working with that. And in general, you gain a lot and a lot of time. You cannot just every time redesign your model from scratch, or at least not today. Or yeah, maybe sometimes in theory it will always be better if we could design the model from scratch and find the best parameters by trying all of the different combinations. But it's well, yeah, it will take an infinite amount of time. um, and and we do not have an infinite amount of time when we're searching for the best network. So yeah, we're starting with something that works and just adapt it the best we can. Yeah, to answer the question in the chat, are there methods that rely images to the corresponding text? Um, oh, yeah, you mean like text extraction, or OCR, or optical character recognition, for example? Maybe, yeah, it will be better if you want to look at keras like this. Yeah, there is some model to, yeah, to extract text from images, or to yeah, read text from images. It's called optical character recognition. You have also some libraries that do that in Python that you can use. For example, Easy OCR, or DocTR, and that you can use, and that works really well. And yeah, you have that indeed in e-commerce websites, to extract some information about a product, about a picture of a product, and write the description, for example. You have that uh, when I don't know, to read some different kinds of paper of finances, or um, yeah, basically any kind of data that's written on the paper, and you can use optical character recognition on it to, yeah, just store or gather data that's on a picture, or on a written document, or on a PDF file, and so on. Um, all right. Yeah, the idea behind layers. Yeah. I will send you a list of links and just at the end, and we'll communicate on maybe on the description or of the video. But it's easy OCR. Yeah, for the packages of OCR. It just a quick word about the way the networks are built and why they are built like this. Is just because it's not the only way. There is, like I'm showing in the past few slides, I just showed this architecture on the right, the multi-layer perceptron, and that's what it's called, the dense neural networks. It's not the only representation. You can have like really exotic networks with what we call skip connection. That means links between layers that are not directly connected, and you can have like layers in parallel, or I don't know. You can do really anything you want as long as you can have some matrix operations to propagate the information from the input to the output. But yeah, it's just much more convenient to have uh, this representation because you can parallelize the computation, and yeah, it just goes really faster when you have this representation, because yeah, you can take a lot of data at a time, at the same time, and just add some columns or rows to your matrix and just have like a bigger matrix um, product. But yeah, it's just really convenient. But you can find some exotic networks, and when you deal, for example, with transfer learning, you want to take like really advanced networks that works well on some kind of data. Sometimes you will find really strange strange networks. For example, you can look at it's called Xception. It's a network designed by Google, I think, and you will see you have hundreds of layers, and I think even hundreds of millions of parameters in the network. So it's yeah, huge, quite huge, and typically that's the kind of model where you cannot do some grid search because it will just not work. Too many parameters, but yeah, it's just convenient to have this representation to parallelize the computations. Yeah, just a quick word about convolution. So we talked about the general representation of the networks and the fact that there is some product between the input data and the weights. And for the images, um, we have as input data matrices of pixels. So we need something more convenient, more intelligent than just having this product between vectors. We need a way to read the groups of pixels that are close to each other. And for that, we use what we call convolution. It's a mathematical operation that's pretty famous and commonly used, even not in deep learning. So it just this product between the weights of the convolution kernel or convolution matrix with your input data, and so it gives you an output with um, the sum of this term by term product. And in that way, we can have the same idea as before. We have a weight, but weights here are not vectors, it's a matrix, and our data is not vectors, it's matrices. So, but yeah, it's exactly the same idea. You have your input data, you have your um, weights that are and you have this product between convolutional product, in that case between the weights and your input data. You may have also an activation function, and you have an output, and this output will be used by the next layer and the next layer, and at the end you will have like some information that you can use as output. And same idea about training, about learning the best weights to extract and to understand the most um, useful information from the original images. And yeah, just a quick parenthesis about pooling. In when you deal with images, you also need to shorten the size and so you may need to just reduce the size by taking most the maximum value or the average value on an area. So that means that just the extracted information from the convolutional matrix from the weight, you will reduce it to just the most important information that you will keep for the next layer. And it's yeah, in a way, it's one kind of activation function, but yeah, it's called pooling. And it's also convenient because yeah, you keep like the most important information or the average of the information on an area of the image, and at the same time you reduce the size for the computations. It's really faster, so that's really useful. And in general, when you have images, you will have networks, complicated networks that look like this, and actually you have a succession of convolution layers and pooling layers, and you just one layer at a time extract the information from the images, and yeah, you just basically extract each time more precise, more specific, more small informations, or sorry, smaller informations, and reduce at the same time the size. So you start with your image, maybe a large image with this representation in color, and at the end you will have something like this. So really tiny bit of information that were extracted by convolution and pooling, and you have a lot of them. You can see it in the depth of this cube or something like a cube, and the depths means the number of information that you got. And so at the end you have all of this information, and you can just take a vector representation of these informations, and based on this vector representation you can use a classical network that you know, and have an output that will give you the classification answer you're looking for example. So that's the idea behind convolutional neural networks, that the networks you use for images. And really it's the same idea. You can yeah, you have this learning, you have this data that goes through the network, and at the end you have a prediction, and based on the prediction and the true expected output, the network will try to learn the best weight. Here it's the best convolutional matrices to extract the most important features of the image. And yeah, you can here have a representation. It's really interesting to look at the features that are learned. It, yeah, may seem a bit strange, but like this convolutional operation, you do that with a lot of different filters, and the network will try to learn the best filters to extract the most important information. And when you have a trained network that works well, the extracted features look like this. You have at first like just yeah, what we call low level features, like just yeah, shapes like this, and at the end you will have really precise information. You can see here the wheels, yeah, some other parts of the vehicle, but the wheels, for example, and just it's yeah, the layers look basically like this. So the networks will just converge towards this kind of learning, this kind of features extraction, and based on that, it will focus on the most important part of the image to answer the problem you want to solve with the images. So yeah, maybe the most important thing here to remember for the convolutional network is the fact that you extract one layer after each. Yeah, one layer after another, you will extract some information and try to use it at the end to predict the output. And yeah, basically it's written exactly in the same way on Keras. Really easy to just create some convolutional layers with a lot of filters, and to add some pooling to reduce the dimension, and you just do that, and at the end you just have a classification here on the different, for example, number of classes you need to predict. And yeah, really easy. 10 lines, and we have a convolutional networks with thousands of parameters and a lot of different filters, and just one step of training after another, the network will try to learn the best weights for its filters to extract the most important information. And it's the idea to remember about deep learning. So I've talked about dense neural networks and convolutional neural networks. You also have recurrent neural networks, and for text data, and recurrent neural networks have this link between different neurons to keep track, let's say, of the time steps, the fact that there is one word after another. You have some more advanced networks that can work in an unsupervised way, so they do not need the target label to train. They just train automatically just understanding the image they're reading. It's called an autoencoder, for example. You have some famous networks for the deepfakes, the GANs, generative adversarial networks that are that trains by trying to they trained in how we could in an adversarial way. That means that there is one network that trains to and tries to beat the other one, and the other network so tries to not get beaten by the first network. So it just learn like this, and it's used to generate like artificial images. It's famous for the deepfakes. You have the autoencoder is used for to reconstruct the data indeed. Can be used for that. Yeah. So you have whole kinds of network, but the general idea stays the same. You have this representation with neurons that will be activated at the certain when they reach a value, and they try to do some prediction, and based on that prediction, will learn the best weights to adjust, to adapt, and to find the best answer. So that's the general idea about basically deep learning. So if it was a bit blurry and seemed magical, it's really not magical. It's really just mathematical, this mathematical operation. And you just have this information that propagates through the networks, and that the networks learn the best weight. But you have a lot of different networks, different approaches, different use cases. So that's really interesting. I will send you some link about OCR and the packages for NLP also, and some references, and if you need any. If you have questions, you can ask me, and otherwise, I think we are done. I didn't go into too much details about this kind of mathematical operation and the way the networks adapt the weights. If you want to take a look at about that, it's called gradient descent. It's classical mathematical techniques that's used in other fields, but here the idea behind the learning is called the gradient descent. So if you want also, maybe I would add a link about that. All right. If you have questions, you can ask me, and otherwise, I wish you a good evening. All right. Seems like there is no questions. Thank you for the question and the messages on the chat. And I will add some more links and references about that. And the real question, we will have another meeting on this topic. Maybe a more advanced version, maybe focused on the way the networks learn, or focused on recurrent neural networks for text data. It could be an idea. We'll try to plan that. If you're following the data scientist track, you should have a lot of courses about deep learning just in the last 2 sprints of the course. All right, great. I will add some links in the description and a link to for our training about deep learning. And great, thank you for the question and your attention during this hour. Hope it was not too hard to understand for this mathematical aspect, but yeah. Thank you, everyone, and I wish you a good evening.